So, hi everybody. Today we're going to be doing a lab on simple harmonic motion. And before we get into the experiment, let's just really quickly recap some of the concepts that we touched on in lecture. So the first thing is a little bit of terminology. I want to define again for you something called periodic motion. What does this mean? So when we say a system is undergoing periodic motion, what we mean is the motion is repeating itself in some kind of fixed time interval. So an example of that would be the Earth's orbit around the sun. When we think about the Earth's orbit around the sun, that is a motion that repeats itself once every year, so it's definitely a periodic motion. When we talk about simple harmonic motion, you want to think of that as a special case of periodic motion. So it does repeat itself in regular time intervals, but beyond that, simple harmonic motion is something we can describe using a sine function. Okay? So let me give you an example of that. The sort of classic example that we've been looking at in lecture for a very long time is a mass on a spring. So you have some kind of mass attached to a spring, you set that in motion, and it's going to vibrate back and forth with a fixed period. Okay, so when we use the word period, what we mean is how long does it take for the motion to repeat itself? In the case of the mass on a spring, how long does it take for the spring to oscillate back and forth one time? Well, in lecture, we developed an equation for the period of a mass on a spring system. And the period given by t is equal to 2 pi divided by the square root of m over k. That's the sort of theoretical formula for the period that we derived in class. Now what we're going to do is put that to the test experimentally. What is the actual period of a mass spring system? Does it fit that definition that we developed in class? Now let's take a look at the experimental setup here. First thing to note is that we have a spring, it's vertically hanging, and directly below that is a motion detector. Now this motion detector is connected to our computer, so any data that's taken here, we can look at it using our computer interface, we can plot it out, we can do all sorts of things with it. And essentially what we're going to do is set the spring in motion by pulling it down like this, then letting it go. Now you see it's bouncing up and down. Now the claim I made earlier is that this is simple harmonic motion, but we can actually see if that's the case by plotting the position of the spring versus time on the screen and seeing if that really looks like a sine curve. And then after that, we can use the data plotted on the screen to tell us what the period of this simple harmonic motion is. Like, so how long does it take to bounce up and down one time? Okay, there's one last little bit of complication here. Throughout the experiment, we're going to be hanging different amounts of weight from the end of the spring and then seeing how that changes the period. Okay, so the more and more weight we hang, what happens to the period? Does it go up? Does it go down? Does it stay the same? You may notice that even when there's no weight hanging from the spring at all, it still bounces up and down. So in our equations, when we talk about the mass hanging from the spring, we actually have two parts of that we want to think about. One is what we're going to call m prime. That would be the effective mass of the spring itself. And the other is what we're going to call m. That's the mass that we attach to the end of the spring. When we talk about the period being 2 pi times the square root of m over k, when we say m, we're really referring to the combined mass of the spring and what we're hanging from the end of it. Okay, so for the first trial of the experiment, we're going to have 50 grams hanging from the end of the spring. And what I'm going to go ahead and do is set it in motion by pulling it down a couple centimeters and then letting go. Then what I'm going to do is hit collect on the computer. And now we're taking data from the motion detector. So notice it's making a clicking noise. The reason for that is the way the motion detector works is it sends a sound wave outwards towards whatever we're measuring the motion of. Some of those sound waves will reflect back into the detector. By measuring that reflected sound wave, it can tell you how far away the object is. And so that's really why you hear those clicks. Okay. Now let's take a look at the data now that it's plotted out here on the screen. So first thing to note is you're looking at a position versus time graph. So position of the hanging mass is plotted here on the vertical axis, and then the time elapsed is plotted here on the horizontal. First thing to notice about this is it does look like what we have is simple harmonic motion. This does look like a sine curve. And we can now measure the period of the motion in the following way. So let's put the cursor right here at a peak in the sine curve, and then we'll drag it all the way over here to the next peak. Okay? Okay, so the first peak represents the beginning of one cycle of oscillation, and then the second peak represents the end of that cycle. So the time in between those two peaks is a period. Now we can directly read that time off the graph, and what we're getting is 0.812 seconds. So when we have a mass of 50 grams hanging from the spring, the period is 0.812 seconds. Okay, for the next run of the experiment, I've added 50 grams to what we had before, so now there's a total of 100 grams hanging from the spring. We're going to do the same exact thing, set it in motion, and then collect data using the motion detector. So here we go. Okay, and now here's that data plotted out on the screen. Again, what you're seeing is a position versus time curve. And in the same way, we can measure the period by just seeing how much time elapses from one peak to the next on this sine curve. So I've selected that region of time. And now what we're getting is 0.919 seconds. So when we have 100 grams hanging from the spring, the period is 0.919 seconds. So notice how now that's a longer period. It's taking longer to bounce up and down the more mass that we add. So the rest of the experiment goes in pretty much the same way. Each trial, we're going to add more mass. We're going to add 50 grams to the end of the spring. We're going to set it in motion, and then we're going to measure the period. And what you're going to find is, as we increase the mass, the period gets longer and longer. So that does make sense intuitively. The more mass is hanging from the end of the spring, the slower it will move. That's what we're going to find. And so we'll keep doing this, adding 50-gram increments until we get to 300 grams. So I'm not going to show you all those trials on the video right now. Just going to flash the rest of the data up on the screen. So here it is. So the next step is to come up with an independent measurement of K, the spring constant, for the spring that we were using in the experiment today. So the way this is going to work is very similar to an experiment we did earlier in the year. Basic idea is this. We're going to start by hanging the spring vertically, like this, measuring its length, and then if we add some weight to the end of it, we'll notice that it stretches out, so the length increases. If we find the difference between those two lengths before we added weight and then after, we can calculate how much it stretched out. By what distance did the spring stretch out? If we add more weight, it'll stretch out even more, and we can measure how much it stretched in that case. So basically the data we're compiling here is the amount of force we're applying to the end of the spring, that's one number, and the amount of stretching that results from that. If we compile this data for many, many different trials, what we can then do is measure the spring constant K. So I'm not going to show you that experiment. Instead, what I'm going to do is show you the data. Just put it up on the screen here, and you're going to use this to calculate the spring constant K for this spring. So that's the experiment. You've seen how it goes, you've seen the different components of it. And now that you've collected all the data from this video, you should be able to do the analysis at home. And the worksheet that accompanies this video explains exactly how to do that analysis. There are two really big results that you'll get from that analysis. The first is you should be able to measure the spring constant using the simple harmonic motion data. So in other words, the way the period depends on the mass is going to give you an estimate of the spring constant K. Now we'll have an independent measurement of the spring constant from that last experiment we did, where we see how much the spring stretches out when we apply a certain amount of force to it. Now, these two different independent measurements of K should end up agreeing to a really close degree of accuracy at the end of the day. So make sure that when you do the analysis, your two spring constants agree with each other. If they don't, please go back and check where you made a mistake. So that's it for today. I'll see you in the next lab video. Until then, be safe out there. Take care.